All right, we'll be looking at the root locus technique. This is a graphical technique and involves a reasonable amount of analysis, but it is a powerful graphical method used in analysis and design of control systems. It provides a technique for determining stability conditions and transient responses. The technique gives a qualitative description of a control system's performance and serves as a quantitative tool for yielding more information than other methods investigated today. Now, the process involves sketching the root locus without having to factor the denominator of the closed loop transfer function, that characteristic equation. The properties of the root locus are able to derive from the general control system. So, okay, there's a general control system. Input, output, of course. We've got some feedback, and of course, we've got our forward transfer function. Okay, so closed loop control transfer function, since it is feedback system, is given by T of S equals K G of S transfer function divided by 1 plus K, the gain, G of S, H of S. That's a typical format for feedback. So a pole, S, exists when the characteristic polynomial, that is, in other words, the denominator, becomes 0. So we can equate that to 0, rearrange that, and this is one of our working conditions. So therefore then, looking at the gain multiplied by G of S transfer function times H of S, that unity feedback, we'll be using unity feedback. Then we can start looking at the manner of these kind of plots that we, basically looking at loci. Now, where -1 is represented in polar form as that, so alternatively, a value of S in a closed loop pole occurs if we take the absolute value of that particular product, and of course then we end up with this interesting relationship. And again, as always, this is the background mathematics, so don't freak out too much. Just hang with it and see how we actually put it into place. So what this particular relationship implies is that if a value of S is substituted into the function K, again, multiplied by the transfer function G of S, multiplied by that feedback H of S, then the complex number will result. If the angle of that complex number is an odd multiple of 180, then that value of S is a system pole for a particular value of gain K. In this case, to satisfy that angle criteria, we have to look at that. So when we do that, of course, we can go and calculate our gain value by rearranging that expression, and our gain will equal 1 divided by the absolute value of the product of G of S, transfer function, multiplied by H of S, the transfer feedback function. Consequently, a pole of a closed loop system causes the angle of K, G of S, H of S to be an odd multiple of 180 degrees. Thus, the magnitude of K, G of S, H of S must be unity, and the implication is that the value of K is the reciprocal of that particular G, S, H of S when the pole value is at that particular value of S that we've determined. So, sketching the root locus, well, I've tried to give you a nice little algorithm. If you follow this and follow the details in terms of providing the background information, then you really can't go too far wrong. So the following rules will give you a sketch with a minimum number of computations. Sometimes, say in an assignment, you might be asked for, say, the major ones, but I'd always suggest to you that you go through and do all steps, because that way you're building up the picture, plus also you have a far better idea of what's going on. Okay, so the first thing we're going to do is these things called the branches, so the number of branches will be determined. Then we'll have a look at the symmetry, the real axis segments, the starting and ending points of our root locus, what happens to the root locus at infinity, what are called break points, break in and break out points, and what happens at the imaginary axis, j omega, and of course plotting the root locus overall once we've gathered this information. So, first thing we need to do, we're going to consider this particular feedback function. As you can see, it's got unity feedback, so H of S is going to be equal to 1, but our transfer function G of S is equal to K into S squared plus 1 divided by S minus 1, S plus 2, S plus 3. So those three factors, nice and easy. Now, again, they won't always be factorized, so you might, before you begin anything, factorize that particular denominator. So just made life a little bit easy for you at the moment. So we're going to sketch the root locus. So the first thing you have to do is the number of branches. And what you'll see here is you need to not just suddenly do a calculation, you need to substantiate it. So therefore then when you're doing these problems, pretty much you can cut and paste these expressions that I've developed out of the textbook. So each closed loop pole moves as the gain is varied. If we define a branch as the path that one pole traverses, then there will be one branch for each closed loop. Again, proper referencing. using the textbook in this case. Thus, the number of branches of the root locus equals the number of closed loop poles. So how do you go about doing that? Well, all you do is go and consider the denominator, and of course, that's the characteristic equation. Equate it to 0, and you can determine your pole. So in that case, it's already been factorized for you, nice and easy. So as you can see, we must have 3 poles, one at s equals 1, one at s equals -2, and the other must be at s equals -3. So there are 3 poles, so there are 3 branches. Easy as that. The next thing is the symmetry. Well, it just depends, but the reality is that you'll always find the symmetries about the real axis. I won't give you any problems that vary from that. So again, this is a pretty straightforward statement that you just need to, include in your solutions to substantiate that, basically. So for symmetry, if the complex closed loop poles do not exist in conjugate pairs, the resulting polynomial, formed by multiplying the factors containing the closed loop poles, would have complex coefficients. Physically, realizable systems cannot have complex coefficients in their transfer functions. Thus, we conclude from, again, give a proper reference. In this case, we're still working with ENEE13019. The root locus is symmetrical about the real axis. So every time you do a problem, if you just state that, as you see, then you've already got your argument, you've got your valid statement. And as I said, they'll always be symmetrical about the real axis. So then we explore that a little bit further, and again, all this kind of commentary, just cut and paste it, make sure you include it. So you're building up your argument, and then as you see, you'll have to do the calculations. So from ENEE13019, let's use the angle property that we were just talking about above to determine where the real axis segment of the root locus exists. Note the following: the angles on the real axis alternate between 0 and 180. That's what happens along the real axis. The angle is 180 for regions of the real axis that exist to the left of an odd number of poles and or zeros. So therefore then, on the real axis, the gain is greater than 0, gain k. The root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. All comes from mathematics. So this is the next important part. So state your general equation and then obviously do your quick calculation, and you'll see you'll end up with these particular values that are showing you what's happening about the real axis. So good idea to go and plot that out now. So we've already figured out what our poles are, 1, -2, and -3. So x's for poles. 0 is where you put a 0, a circle there for poles. And we've already indicated that this is what's happening because we've been able to see from the calculations above. Sorry, this is of course our imaginary axis, the j omega axis, and this of course is our real axis, the sigma axis. Starting and ending points, well, from again the ENEE13019, the reference book, the root locus begins at the finite and infinite poles of g, s, h of s, and ends at the finite and infinite zeros of g of s, h of s. So in our case, the poles are located at s equals 1, s equals -2, and s equals -3. Now consider the numerator now, that's how we got that finding out 0. So equate that to 0, and as you can see, we're going to end up with s equals positive j or negative j. So there are 2 finite, they're not infinite, they're 2 finite complex zeros, positive j and negative j. Now the root locus begins at the poles, positive 1, -2, and -3, and ends at the zeros, which we just calculated, positive j and negative j. Thus, the poles start at 1 and -2 and move through the real axis space between these 2 poles. They meet somewhere between these 2 poles and break out into the complex plane, moving as a conjugate. Remember that bit about the conjugate we talked about beforehand. The poles return to the real axis somewhere near -3, which is that 3rd pole. Behavior at infinity. Well, again, ENEE13019 tells us that a function can have infinite poles and zeros. And if the function approaches infinity as s approaches infinity, then the function has a pole at infinity. If the function approaches 0 as s approaches infinity, then the function has a 0 at infinity. Every function of s has an equal number of poles and zeros. If we conclude the infinite poles and zeros as well as the finite poles and zeros. So it's very, very important that we go about finding what happens as infinity so we can include those infinite poles and zeros. So what we're doing is we go back to our original transfer function g of s, and what we're going to do is see what happens as s gets bigger and bigger. So what happens when s approaches infinity? So we plug in our infinity values, do a quick calculation, so that's infinity squared, we've got infinity times infinity times infinity, infinity cubed. So basically, as you can see, as s tends towards infinity, then g of s tends towards 0. So therefore, g of s has a 0 at infinity. Now, note that every function, as we said, of s has an equal number of poles and zeros. So it's a good idea to jot these things down. So you follow this process exactly, and you'll find that everything will just drop back by nicely. So noting again that every function of S has an equal number of poles and zeros if we include the infinite poles and zeros as well as the finite poles and zeros. So it's always a good idea to write them down so you can keep track of them. So we calculated 3 finite poles, 1, -2, and 3. We have no infinite poles. Finite zeros, we have 2, J, positive J and negative J, and of course, we just calculated above, we have 1 infinite zero, which is at 1. So in our case, we have 3 poles, all finite, and 3 zeros, 2 are finite, and 1 are infinite. Thus, for G of S, the root locus begins at those finite poles of G, that little expression, that multiple, K, again, G of S, the transfer function, times the feedback H of S, and ends at the finite and infinite zeros. So the question remains, where is the infinite zero? We must know where this zero is in order to show that the locus is moving from the 3 finite poles to the 3 zeros. Again, remember that 2 finite and 1 infinite zeros. The following rule helps us to determine this zero in infinity. This rule also helps us to locate the poles at infinity for functions containing more finite zeros than finite poles. Noting, again, this comes from ENEE13019, for physical systems, however, have more finite poles than finite zeros, since the implied differentiation yields infinite output for discontinuous input functions such as step functions. The rule tells us what the root locus looks like as it approaches zeros at infinity or as it moves from poles to infinity. So again, this is mathematical theory. If you find that gobbledygooky, just follow through the process and you'll see that the application of the mathematics does make more sense as you go. And we plot this out. So the root locus approaches a straight line as asymptotes as the locus approaches infinity, and further the equation of the asymptotes is given by the real axis intercept at sigma subscript a, and that occurs at some angle theta a as follows. So you do this calculation here, looking at the sum of finite poles minus the sum of finite zeros, divided by the number of finite poles, divided by the number of finite zeros, to find our real axis intercept. And to find that angle, theta a, then we use this little formula, 2k plus 1 pi, where k is equal to 0, plus or minus 1, plus or minus 2, minus 3. Plug that in, do your calculation. So again, we're dividing then by the finite number of poles minus the number of finite zeros. So the angle is given in radians, and with respect to the positive extension of the real axis. Note that the running index k yields a multiplicity of lines that account for the many branches of root locus that approach infinity. And again, we've got a simple example here, but when you go through and do the examples, tutorial problems, you'll find that that gives you other insights as well to some of those things, in particular those things plus other things. Now in our case, we have 2 finite zeros. Remember, at positive j and at negative j, and 3 finite poles at positive 1, negative 2, and negative 3. So to find that intercept value, plug it in the formula, and we find that that's negative 4. Find the angle occurring at that particular intercept. And again, as we see, we're going to calculate multiple asymptotes because our k value varies from 0, 1, 2, because we have 3 of them. So as you do that, you see you've got finite poles minus finite zeros, 3 minus 2, so you're only going as far as k equals 2. So when you do that, you've got an asymptote occurring at these angles of pi, 3 pi, and 5 pi. So this indicates that the locus begins at the open loop poles and ends at the open loop zeros. Again, this is all just bits of information. You'll see that finally we'll put it all together and be able to plot out our root locus. A root locus is just a graph. It's just a fancy way to say that we've got a range of points that we're plotting out. Again, root locus is a mathematical expression. So again, when you're doing your solution, write out these little statements and do the calculations that are specific to your particular problem. So from these, numerous root loci appear in the breakaway from the real axis as the system poles move from that real axis into the complex plane. Now at other times, the loci appear to return, they break in, so break out or break in, to the real axis as a pair of complex poles become real. So you can do that calculation. That's our expression in this case. Now for all points on the root locus, k, g of s, h of s equals -1, and along the real axis, s equals sigma. So basically we put in our sigma values, we can solve for k, just rearrange, and then we can differentiate. Now since this is, and again this is back from high school maths, but first year maths as well, so you should be quite competent in this. It's a quotation, so you need to use the quotation rule for differentiation. So we go about doing that, and we'll break it up into little ones. So we'll take the expression u, and again, just multiply it out. It's much easier as an expression. Then we take the derivative, and our v term, of course, is our denominator. Take the derivative, and then we can plug it straight in the formula nice and easily. So we pick up those things, put them in that formula, do our mathematics, and again, what we're interested in is that by setting the derivative to 0, we're going to determine the maximum minimum gain. That's what you always do when you max and mins when you're doing a derivative. And hence the break-in and breakaway point. So equate that to 0. So now we have an expression which is to the 4th power. Now, since it's to the 4th power, how do you go about doing that? Well, yes, you can shove it in your mathematical calculator and do that, or you could use some mathematical program. That's fine, but the point of the matter is you need to demonstrate how you go about doing that. There is another method you can use. It works just as well, but the point is that you can use this expression here. But you'll end up with exactly the same expression that you calculate, just a different way of doing it. And again, you'll still have to, to figure out that 4th order. So here, we've gone through using the calculator. Since these are both complex numbers, then neither of them lie on the real axis because obviously they're complex. So there's no break points. So that means there's no break-in points and there's no breakaway points. All right. Then find the range for stability for the unity feedback system. Well, here's our system. There's our g of s function. And so we're using unity feedback. So go through and find out what that looks like as a feedback system. Follow the mathematics through. It's a lot of just doing, as you can see, getting common denominators, then flipping that over, and then here's our expression. This now takes into account that we've got a feedback system, and that's the proper expression. So here, again, as always, we're interested in the characteristic equation because that tells us things about the function. In this case, we're trying to find some more information about the gain. So the denominator is the polynomial of interest, and again, we can use that Roth-Hurwitz criterion. We can apply that to the characteristic equation and go about finding information about our gain. So just like we've done beforehand, we write down as we go through. We can see we're starting with the highest power, which is S3. So we do each alternative term. So that will be the coefficient is 1, and then the alternative term, the coefficient is 1. Then we move to the next term, so that's the S squared, and again, its coefficient is 4 plus K. And likewise, we then go to the next alternative, which is K minus 6 as a coefficient. So we need to generate S1 and we need to generate S0 rows. Just like we've done beforehand, we have to go about using this as the pivot, and then we've got this little determinant to calculate. Go back and revise the Roth-Hurwitz if you haven't remembered the process overall, but basically I'll do the full process here that should keep track of everything. So as you go through, you then need to move on to the next part, and again evaluate that, and then finally organize the S0 row. So we're going to calculate this first term here, and then as we go through, we can see that we get a little expression here. So for positive values gained, those for which the root locus is plotted, only the S0 row can actually yield a row of zeros. So when you do that, we've got K minus 6, so that equals 0. That's how we evaluate it. So therefore our gain must be 6. So forming the even polynomial by using our S2 row, like we've done beforehand. Again, if you haven't done the Roth-Hurwitz for a little while, go back, have a look at how we go about that process, and all the rules are there. You need to revise them if you're not too sure. We plug in our value for our gain, and we end up with a value of S equals 0. So therefore, the root locus crosses the J omega axis, or the imaginary axis, at the origin with a gain of 6. So we conclude that the system is stable because K, the gain, is greater than 6, greater than 0. It's got to be a positive value. So the next step is that looking at that information, the J omega axis crossing is the point on the root locus that separates the stable operation of the system from the unstable operation. The value of omega at the axis cross over that axis yields the frequency of the oscillation, while the gain at the axis crossing, the imaginary crossing, yields information about the system's stability. For instance, instability at small values of gain and stability at large values of gain. Now, to find that J omega axis crossing, we can use the Roth-Hurwitz criterion, forcing a row of zeros into the Roth-Hurwitz table, which is just basically basically what we did in the last step. So this is just putting it all together, giving a little bit of expression to the significance of that particular calculation. So forcing a row of zeros in the Roth-Hurwitz will yield the gain. Going back one row to the even polynomial and solving for the roots will yield the frequency of the imaginary axis crossing. And then from parts C above, in determining the value of K, that will make the system marginally stable for the unity feedback system. And in this case, that was determined that the root locus crosses the imaginary axis, J omega, at the origin at a gain of 6. So really this is, if you're making tidy up what we did in step 6, it's just basically a general description. As I say, that's the theoretical background, that's the justification, so include that in your solution as well. So when you plot it out, we can see we've got a zeros at 1 and -1, so that's, if you remember, that was positive 1j, so that's the j axis, remember, and at the -1 j, so therefore then pretty much that's our root locus for that. Now our root locus has become far more interesting, that they can look like parabolas and they can look like you know, a whole range of interesting shapes, but as you get in and do the exercise, you'll see those come up quite readily, and also just by following the due process that I've outlined. If you do that as a bare minimum with the expressions and the justification, you'll find that you'll do quite well in plotting out the root locus. Now, the key thing is that we've been talking about the root locus in the analog you know, world, but if we look at it in the digital world, you can also use this particular technique to help us do that for the Z plane, and also, of course, that means that we're working in the digital systems. And as I said beforehand, a lot of these analog processes translate into the digital because as control systems has evolved, they've tested them out and said, well, okay, if the system is going to operate, then it should be able to be seen to be operating in the digital context as well. Stability is stability, and then there are some characteristics related to digital that get drawn out as well. So we've seen for the analog system, a transient response requirement was specified by selecting a closed loop S-plane pole. We've discussed, chapter 8, how the closed loop was on the existing root locus and the design considered a simple gain adjustment. The closed loop pole was not on the existing root locus, then a cascade compensator was designed to reshape the original root locus to go through the desired closed loop pole. A gain adjustment then completed the design. We'll investigate and apply similar techniques for application in digital systems. Here we'll concentrate upon design via gain adjustment. Designer compensation will be left to a higher level unit. Previously in chapter 4, we outlined the establishment of the relationship between a transient response and the S-plane. So vertical lines on the S-plane were lines of constant settling time. Horizontal lines were lines of constant peak time, and radial lines were lines of constant percentage overshoot. To draw equivalent conclusions on the Z-plane, we'll need to map those lines through this expression Z equals e to the st. So again, this is the mathematical background. We're going to apply it, so just bear with it. Again, as always, if you find mathematics a bit gobbledygooky. Then the vertical lines on the S-plane are lines of settling time and are characterized by the equation S equals sigma 1 plus j omega, where the real part, sigma 1, is equal to -4 Ts, which you should remember relates to our formula for settling time. So it's constant and is in the left half plane for stability. Now, substituting this into our little expression for Z equals e to the st will result in Z1 equals, again in polar form, e to the sigma 1 t multiplied by e to the j omega t, which equals R1 e to the j omega t. And again, this is all first year mathematics. If you're a little bit unsure of that, you need to brush up on your first year mathematics. This equation represents concentric circles of radius R1. So if sigma 1 is positive, the circle has a larger radius than the unit circle. On the other hand, if sigma 1 is negative, the circle has a lower radius than the unit circle. The circles of constant settling time normalized to the sampling interval is demonstrated in this figure below. So this is a stock standard device, if you like, a graph, to help you analyze those particular processes. So again, it just depends on what your damping ratio is. But this has quite a useful purpose. In this figure, the concentric circles have a radius of e to the sigma 1 t, which equals e to the -4 divided by ts on t. Also, ts on t, settling time, equals -4 over the log of r, where r is the radius of the circle of constant settling time. All now it's just justifying the mathematical background of the graphical form. The horizontal lines are lines of constant peak time. The lines are characterized by the equation S equals sigma plus j omega 1, where the imaginary part, omega 1, is equal to pi over Tp, which is constant. Tp is the peak time. Substituting this again into our expression for z equals st results in this polar form of z equals e to the sigma t multiplied by the exponential e to the power of j omega 1 t, which is our timing interval, equals again e to the sigma t, e to the j theta 1. This represents the radial lines at an angle of theta 1. If sigma is negative, that section of the radial line lies inside the inner circle. If sigma is positive, that section of the radial line lies outside the inner circle. The lines of constant peak time normalize to the sampling interval as shown in the figure below, and the angle of each radial line is omega 1 t, which equals theta 1, which equals pi divided by Tp over t, from which t divided by p on t equals pi divided by theta 1. Finally, we map the radial lines of the S-plane onto the Z-plane. Remember, these radial lines are lines of constant percentage overshoot on the S-plane. Show in the figure below, as we showed, this radial lines are represented by that. So again, this is nothing new. You should recognize that expression from earlier, back in chapter 4 or something, when we were defining overshoot and settling time and that type of thing. So basically what we're saying is that when we plot all that out, we can get this particular form, then transforming that expression for S to the Z plane will yield these expressions. Thus, given the desired damping ratio, this expression for Z can be plotted on the Z plane through a range of omega t, as shown in the figure of concentric circles shown previously. Those ones above. These curves can then be used as a constant percentage overshoot curves on the Z plane. This section has set the stage for the analysis and design of transient response of digital systems. In the next section, we're going to obviously plot them. So this is the key thing. There's your mathematical background. Don't freak out. Come and have a look at how we go about using those in a practical context. Here we're investigating plotting the root locus and determining the gain required to attain stability, as well as the gain necessary to meet transient response requirements. The open and closed loop transfer functions for the generic digital or discrete system, given below in that little figure, are identical to that for a analog or a continuous system, except for a change in the variables. Obviously, we're dealing with S with the analog system and Z with the digital system. Now, we can adopt the same rules for plotting the root locus. There's nothing new there. As I say, these processes generally translate across. So we previously discussed in the last section how we derive curves of constant settling time, peak time, and damping ratio. In order to design a digital system for transient response, we find the intersection of the root locus with the appropriate curves as they appear on the Z plane, as in the figure in the previous section, which highlighted the concentric circles. All right, so for digital control systems, when you're sketching the root locus, the following rules yield a sketch using the minimum computation. So again, follow exactly the due process that I've outlined, and you won't have a problem. Well, to minimize your problems. Determine the number of branches, in other words, find the poles. Determine the starting ending points, so you find your zeros. Behavior at infinity, determine the breakpoints. Draw a new unit circle and trace out starting and ending points, which are symmetrical about the x-axis. Consider your poles at when the gain is 0 and zeros when the gain is infinite. Determine the values of k for which the system is stable, and determine the crossover points. And then finally review, refine, finalize your information and sketch the root locus. All right, and again, as we go along, I'll give you some helpful hints and just show you the process is not that arduous, to be honest. So sketch the root locus for this system and determine the range of k, gain, for stability from the root locus. So here we are, a digital system. We've got unity feedback system, just as we've had before with the analog system. But our transfer function is k into z plus 1 divided by z minus 1 over z minus 0.5. Now again, I've already factorized it for you, but keep in mind that that won't always occur. You might have to, well, if it hasn't, you will definitely have to go through and factorize it. So we're going to consider that particular transfer function, t of z equal to k into z plus 1 divided by z minus 1 times z minus 5. So exactly the same idea as we've done beforehand. Follow this particular expressions, and you'll find that we're going to go and find the poles. So again, it's the characteristic equation, the denominator of that particular transfer function equated to 0. Go and find, in that case, your poles. So since there are 2 poles, there are 2 branches. Let's have a look at our starting and ending points. Well, again, from Nice, again, state these, write out these statements when you're doing your solution. The root locus begins at the finite and infinite poles of T, Z, H, Z, and ends at the finite and infinite zeros of T, Z, H, Z. Remember, we're dealing with Z's now. So it's exactly the same expression that we had for the analog ones, whereas we had G of S and H of S in that case. So in our case, we already know that our poles are located at Z equals 1 and Z equals 0.5. So we consider the numerator now. So set that to 0, and as you can see, we find that we have one finite real 0 at Z equals -1. The root locus begins at the poles 1 and 0.5 and ends at 0, -1. Thus, the pole starts at 1 and move through the real axis space to 0.5, and these poles, between these poles, they meet somewhere between these two poles, so somewhere in here they meet up, and then break out into the complex plane, moving as a conjugate, positive J and negative J, and then the poles return to the real axis somewhere over here. So they disappear up here somewhere, disappear out here somewhere, disappear up that way, down that way, and are going to reappear over here somewhere. That's just mathematical behavior. So if we look closely at the behavior of infinity, then again, the statement from ENEE is that a function can have infinite poles and zeros. If the function approaches infinity at S, approaches infinity, then the function has a pole at infinity. If the function approaches 0 as S approaches infinity, then the function has a 0 at infinity. Every function of S has an equal number of poles and zeros if we include the infinite poles and zeros as well as the finite poles and zeros. So no different to what we talked about beforehand. Here we're looking at what happens to Z as approaches to infinity and what happens to our transfer function, just like we did beforehand, plug in what happens particularly at infinity, and we see that again as the transfer function tends towards 0, Z towards infinity, then our transfer function T of Z has zeros at infinity. Note, every function of S has an equal number of poles and zeros if we include the finite poles and zeros as well as the infinite poles and zeros as well as the finite poles and zeros. So we figured out that the number of finite poles equals 2, namely 1 and 0.5. The number of infinite poles is 0. Don't have any. The number of finite zeros is 1, -1. And the number of infinite zeros is 1 because that occurs in infinity. So in our case, we have 2 poles, all are finite, and 2 zeros, 1's finite and 1 is infinite. Determine your breakpoints, just like we've done beforehand. From ENEE, numerous root loci appear to break away from the real axis as the system poles move from the real axis to the complex plane. At other times, the loci appear to return, breaking points, to the real axis as a pair of complex poles which become real. So again, looking at that expression, so for all points on the root locus, K, G, Z, H, Z equals -1. So obviously along the real axis, Z equals sigma. Plug in our values. We can do our differentiation again like we did beforehand. This is a quotient rule because here's a quotient. We need to be able to find the derivative of that. Likewise, we set our U values, V values, do them as little sums. And then once you've done that, you can plug them into your formula, follow the same process. And again, as always, when we're going to determine the minimum maximum of our derivative, we set it to 0. So in this case, we're in luck because this is just a nice little quadratic. We can solve that to find the roots just by using the quadratic formula, if you like. So when you do that, always state your general equation, plug your numbers in, do your mathematics, check, double check, of course, and then we're going to end up with these 2 particular values. Now, okay, just because we've got some values, we don't know if they're break-in, break-out points, or whether they are actually valid in any case. So as we go through, we can test. So for sigma equal to -2.7321, we put it back into our expression, and we get a positive value. Very good. If we take our positive value, again, do exactly the same thing, put it into the expression, we end up with a positive value. So in other words, both are breakpoints as they lie in a valid region for positive gain. In other words, K is greater than 0. And in particular, in considering the information above about that root locus, we're able to also state that this is a break-in point as the root locus returns to the real axis at that point, when we look physically at what's going on, and the breakaway point as the root locus leaves the real axis at that point. All right, so now the value of K at the breakaway point and break-in points, we just take, all we have to do is take the magnitude of those values now. So it's exactly the same calculation, except now we're going to take the magnitude. So we do that. So as you might imagine, we obviously end up with positive values. So done that for each of our sigma values. So draw in the unit circle and trace out the starting and ending points. And remember, it's symmetrical about the x-axis, and consider the poles poles occur when k, the gain is 0, and zeros occur when the gain equals infinity. So let's just zoom in a little bit there, just to get a better, let's put it all on one page so we can see a bit better. So when we do that, so we've figured out that here's our poles, and here's our 0, and we said beforehand these tend towards each other. Some break away, some break in, so they're breaking away from the real axis, these ones, and they're going to end up over here somewhere because they're going to break in along the axis here somewhere and come back into that 0. So what happens out here, we're not too sure, but at least we've got an idea. So that diagram is just demonstrating, as you can see, that one goes to the finite 0, and one goes to the infinite 0 at infinity out here somewhere. And as I say, you'll have to fiddle around with this diagram, don't be too concerned, but if you follow this due process and map it as you go, then the analysis will help you build your argument. So that's basically the information we've gathered so far. Now, after investigating the behavior infinity, we see now that the root locus returns to the real axis and moves toward the finite 0 and infinite 0. So it's important to update your initial sketch, which we just did. So we've done that by putting that unit circle in and making those arrows obvious. Now we've got to go through and we can calculate the gain. Okay, so if I do that, we've got our unity function again, go through, do our unity feedback. And then as we go through, we can see that once we are able to do that calculation, there's our characteristic equation. Now, a couple of things. Sometimes it's a bit hit and miss, so it's a good idea to look at this thing called a jury test. So the jury test, we take that characteristic equation and we apply the jury test to it. Now that's of the form, as you can see, a0 z squared plus a1z plus a2, where obviously a0 equals 1, a1 equals k minus 1.5, and a2 equals k plus 0.5. So condition 1 is we can find the absolute value of our an coefficient is less than our a0 coefficient. So we do that. As you can see, we just do our comparisons. So we reject that negative value, so k is less than 0.5. Then condition 2 for the jury test is that p1, the polynomial at z equals 1, must be greater than 0. So plug your numbers in. Okay, so yep, it is. It's greater than 0. That's fine. And the condition 3 is that when you find your value polynomial at z equals -1, it also has to be greater than 0. So the 1 and -1, of course, relate to the unit circle. So if you think about it, the largest on the unit circle, the largest z value is at the 1s on either either positive point, and -1 and -j in the -1. So that's why it's -1. So also that's greater than 0. So consequently, the system is stable over the range of values from 0 to 0.5, and resulting in the marginal stability obviously is going to be occurring at 0.5. You will find sometimes that neither the jury test nor the Roth-Hurwitz criterion provide the complete information. So you'll need to consider both processes and analyze the results to determine the gain values to which the system is stable. Okay, so then if you do it by the Roth-Hurwitz, you only have to do one or the other, but sometimes the mathematics lets you down with your analysis. So I've done both methods, so just keep that in mind. So exactly the same thing as we've done beforehand. Take the characteristic equation with the Roth-Hurwitz process. We start generating our table, and of course we're looking at z squared, so a coefficient of that is 1. We take the next alternative, so that's k plus 5 is the coefficient. Then we look for z1 row is the k minus 1.5, and then the next alternative term is 0. So then we've got to calculate z0, so we just follow our due process with Roth-Hurwitz. Looking at our pivot point, we're able to calculate, in this case, that that's k plus 0.5 for that term. And then likewise, we're looking at the next expression. So we end up with this as our Roth-Hurwitz. So for positive gain, for those which the root locus is plotted, only the S1 row can yield a row of zeros. Therefore, we need to solve that. So we can solve that. Choosing the positive values, we choose that. So also we can see. So now, ultimately, we will get the same response. But as I say, you choose either, but if you get misleading information, go then and go and apply the other one. So in this case, it's worked out okay. So in this case, when we determine the crossover points where the root locus and the unit circle intersect, the area where the system is exhibiting marginal stability, you can use the margin stability value obtained by both processes. As I say, use one or the other, but when you use one and if it becomes conflicting information, go and use the other process. And that way you'll have a foolproof kind of way at least to make sure that you are covering the process. Determine the crossover points. Well, like we've done beforehand, in this case we're looking at crossover points which are the root locus and the imaginary axis of the Z plane. So in general, Z equals A plus JB, and when the root locus crosses the imaginary axis on the Z plane, then the real part becomes 0, A equals 0, and Z equals JB, because it's obviously crossing the imaginary axis. Substitute this value, so you do that, and then basically if you concentrate on the real parts and the imaginary parts, you can then go through and solve to find your K value, and also solve your B value. So ultimately you can find out what the form of that particular point is, where it's crossing, where the root locus is crossing the imaginary axis. So in this case, the crossover points where the root locus and the imaginary axis intersect occur with a gain of K equals 1.5, and there's our two values that we've been able to calculate. All right. So as we go through, consider now, the second thing to consider is the crossover points, which is the root locus and the unit circle. So consider the gain we got obtained from, either the jury test or the Roth-Hurwitz, as I said beforehand, and that we figured out was the gain was equal to 0.5. So you consider your unit feedback. So therefore, then taking that particular characteristic equation, determine the roots of that characteristic equation at the gain, which makes the system marginally stable, which will provide the crossover points where the root locus and the unit circle intersect. So plug in your, in this case, as you can see, you can plug in your values of 1.5, 0.5. And in particular, we're saying that the gain is K equals 0.5, so we've got our correct expression. Plug in that, and as you can see, we end up again, nice little quadratic, not too terrible to solve. Put it into, again, always write down your general equation, plug in your numbers, and we're going to end up here with these particular two terms. And this is the crossover points where the root locus and the unit circle intersect. And they occur at a gain at 0.5 at those two particular points. All right. Now, the angle of orientation of the crossover points occur at a gain of that. So if you look at it in orientation, pretty much you can do your calculations just like that. So again, what we're doing is gathering all these little bits of information, and then we're going to put them all together. So we go back now. Remember, the last thing is to review and refine. So with the step we wrote beforehand, we had the unit circle. We had some information about what was happening at the poles and the 0. We saw that they were moving towards each other, and we had a breakaway and breakaway points occurring here, and then we had break-in points occurring over here. So now what we've been doing is looking at what happens when, when the unit circle at the crossover point with the root locus, and so what happened to the root locus when it crossed the imaginary axis. So that was the information we were just collecting beforehand. So now we can plot all those out. And what's a good idea is that as you do that, as you can see, state it as, what it is. Well, we're talking about a 0 at Z equals -1, and the gain at all the zeros is going to be infinity. And likewise, let's take this one here, the breakaway point. Then, as you can see, that Z equals positive 0.7321 with a gain of K equals 0.1332. So if you do that, really what we're showing is the information that we've gathered, collectively putting together, and now we have a representation of the root locus for this particular transfer function. All right. What about another example? So for this digital system, you might have to find other information as well. So in this case here, we're given some specific design parameters. So for the transfer function K into Z plus 1 over Z minus 1, Z minus a half, with, as you can see, unity feedback, then the gain K to yield a damping ratio of 0.7 and a peak time TP over T of 10, and the system response of CZ for a unit step sample input of RZ. So First of all, determine the gain K to yield that damping ratio. So all we do is go back to our original transfer function. This is what we know about it. We know we've got unity feedback, so let's go and find our feedback form for that transfer function for unity feedback. Again, that's our characteristic equation. And we come back now and we say we will be determining the gain K required to meet the operational characteristics indicated. In this case, owing to the design characteristics we have been provided with, we will adopt that design chart that you should recognize from before. All right, so what we do is we've got a damping ratio of 0.7. So we're going to go along that line. And we've also got a peak time of TP over 10. So that's this particular line coming through here. That's all well and good. So therefore, then we can read off this particular value, which will enable us to continue with our calculations. So that intersection between the damping ratio line and that particular TP, the TP over T being 10, which was the other parameter, occurs at, again, you know, it's how good you read off these things and how accurate they are, but roughly around about 0.7 plus 0.21 J. So this correlates to D of Z, so we plug that in as our known value, go through, collect up our, just be careful as you mull through with your J's and things like that, make sure you collect them up correctly. So as you do that, we're going to end up with this little polynomial. So again, we're going through and finding that as we equate those particular terms, we find that ultimately we have a gain of equal to 0.06. We'll meet our design characteristics of a damping ratio of 0.7 and a peak time TP over T equaling 10. All right, good. Determine the system's response, C of Z, for a unit step sample input R of Z. So go back, we've got our transfer function, our overall transfer function. It's a feedback system, of course. So we're still concentrating on, in this case, a unit step input. So let's put that in there. And as you see, for a gain of 0.6, we're able to determine the system's response. So C of Z equals to R of Z, G of Z divided by 1 plus G of Z, H of Z. Again, just some manipulation. Plug in our particular expressions. We're going to go through and multiply. And again, as you can see, we end up with a transfer function. And interesting, what we're going to try and see what happens if there are other design characteristics required. But before we do that, that's you've just been able to follow those characteristics, so that will be your overall transfer function for a unit step input. Now, at other times, owing to the design characteristics, we'll need to use other design charts. So, and again, they're readily found. The textbook doesn't obviously give them all. We've already done that particular one in that previous example. But you will need to go looking, you know, other sources, the web, whatever it might be. And this is, I'll just give you an example here. This is, you know, the types of forms that you'll see. So just keep in mind that one textbook can't give you everything, but you might find that you will have to go looking for other ones. This one here, as you can see, gives us some information about the natural frequency and the damping ratio. All right. As I say, the best thing to do with control systems, since it's a mathematical unit, you must get in and do the problems. You must work through, because you can't read about mathematics. You have to do mathematics. And likewise with control systems and that analysis, since it is highly mathematical, you need to go through and do the problems and work through. Now, I've given those complete you know, descriptions, so you should be able to, and again, some nice little algorithms there. So it should work out quite well if you follow what I've been trying to demonstrate to you.